So we've now formulated this constrained optimization problem. It's an optimization problem, but it's subject to this constraint that x plus y has to equal 20. The question is, how do we do this? Well, the method or the mathematical technique that we use is called the method of Lagrange multipliers. And this method is vastly mathematical, so we're not going to get into all the mathematical details, but I will show you here how we can solve a problem like this and how it's done. If you're interested in the mathematical details, there are plenty of videos out there that go into it, but it does get into some multivariate calculus, which would be considered a Calculus 3 class. This is not intended for our audience in terms of getting into that mathematics at this point. So, okay, here's how this works. So we're going to set up a system of equations. So set up a system of equations. And they're not going to be linear, but the system of equations looks like this. What we're going to do is we're going to set up a vector equation, and we are going to refer to our objective function. We're going to refer to this as the objective function. And for nomenclature, we usually, in the Lagrange problem, call this f of xy. Now, the portion of the constraint that is not constant, we see that the constraint function is going to have a constant on one side of the equation. The left-hand side where the function shows up is what we often refer to as g of xy. And to set up the system of equations, what we do is we form a matrix equation. And in the first matrix, what we have is we have the first partial with respect to x of f of x, and the first partial with respect to y of f of xy. And we set that equal to this thing called the Lagrange multiplier. The Lagrange multiplier here, this is the symbol lambda. This is a Greek symbol lambda. It's just a constant. We don't need to worry about its meaning at this point. Lambda is just sort of this new variable that we're introducing. And the only reason we use a Greek symbol here is just to distinguish it from the variables that we're typically interested in solving for, which are x and y. So the use of lambda is not important. You could call this w if you wanted to, but we often use lambda. Now, what we set that equal to is lambda times the partial derivatives of g with respect to x of xy, and the partial derivative of g with respect to y of xy. And then our third equation, so this is actually going to lead us to two equations right here, and I'll describe those in a moment. Our third equation is the actual constraint itself, x plus y equals 20. All right, so we get three equations here. The system of equations that we get are the partial of x, or partial of f with respect to x, equals lambda times the partial of g with respect to x. And the second equation that we get is the partial of y, partial of f with respect to y, equals lambda times the partial of g with respect to y. And then our constraint, g of xy, equals the constant c. Okay, so this constant c right here, that is going to be the constant value that we get in our constraint. Now, g of xy doesn't always have to be x plus y. That's why I'm writing it in this generic form. So we get a system of three equations, and there are three variables here. What are they? Well, the three variables, well, the two that we're interested in are the values of x and of y, but we're also going to end up inadvertently solving for this constant lambda. Lambda does have a meaning, though we won't focus on its meaning here. And then we're going to focus on actually taking this and using technology to solve this system of equations for us. All right. So we could, again, use something like Wolfram alpha or some sort of technology to compute our partials. But for us, that's simple enough. The partial of this guy with respect to x will be f sub x of xy is negative 2x plus 20. The derivative of a constant is 0. And because we're taking the derivative with respect to x, the derivative of y squared, 40y, negative 400, and 20,000 will all be 0. And we're going to set that equal to lambda times the derivative of g of x. Now g of xy is x plus y, and its derivative, the derivative of x is 1, the derivative of y is 0. So this is just going to be lambda times 1. Now, our equation 2 will be the derivative of f, so that's our objective function with respect to y. This is going to be 0 because we're holding x constant. This will be 0. This will be 0. The derivative of negative y squared is negative 2y. The derivative of 40y is 40. The derivative of negative 400 is 0, and the derivative of 20,000 is also 0. We're going to set that equal to this variable called lambda times the derivative of g with respect to y. So the derivative of x plus y, well, the derivative of x is 0 with respect to y, and the derivative of y is 1. So that also comes out to be 1. And then our constraint function is going to be x plus y equals 20. Now, once again, the partials of negative x squared plus all of this stuff we can do with technology. And so here we can see that the derivative of this function is in fact 20 minus 2x, or negative 2x plus 20. And then we could also type in here, replace this with partial derivatives, and it would give us both of them. But if we just want them one at a time, we can say d dx and then d dy. And now if we take the derivative with respect to y, we get negative 2y plus 40, which is exactly what we obtained here. Okay, now we can take the derivatives of x plus y, which is our g of xy with respect to x, and we'll get 1. And then the derivative with respect to y of x plus y will also be 1. So that's a more rapid way we could have done this. And then our third constraint is x plus y equals 20. So now what I'm going to do is I'm going to solve this system, negative 2x plus 20 equals lambda. Okay, how do we get a lambda in here? Well, I like to just use a capital L. You can also use the extended keyboard here, and you can find the symbol lambda, which is, where is it? Where is lambda? Lambda is here. You can see that says lambda, or you could actually type in the word lambda, but we can just use L times 1, and then we have negative 2y plus 40 equals lambda, and then x plus y equals 20. All right, so what any strong piece of technology will interpret this to mean is solve this system of 3 equations containing 3 variables and give me back the values of those 3 variables. So hopefully we'll get what we expected, hide that extended keyboard, and we get, lo and behold, x equals 5, y equals 15. Now, it gives us a value of the lambda as well. It says lambda equals 10, but we're not going to use that at this moment. It does have a meaning, and it can be a useful meaning, but we're not going to get into that here. All right, so that means that I have a critical point at x comma y equals 5 comma 15, which is the exact same value that we have up here. This is the point 5 comma 15, and then if we were to plug 5 and 15 back into our profit function, we would see that that would lead to a profit of 19,500. How do we know for a fact that it is a maximum and not a minimum? The question we have to answer next is, how do we know that 515 comma $19,950 is a maximum. How do we know that we didn't find a minimum? Well, if we go back up to the graph, we can visually see, at least it appears, that that lies on a maximum. And the two-dimensional kind of slice that we've created, if we imagine that that blue line is where we take that surface and we slice it in two, then if we were to look at the outer edge of either one of those slices, we would notice something that looks pretty parabolic. So from visual inspection, we think it's a maximum, but in order to be absolutely sure, because a lot of times visual technology can fail us. So a powerful technique is to go ahead and assess whether this point is in fact a max. So we're saying that 5 units of product 1, 15 units of product 2 will yield us a profit of $19,950. So in order to check this, we cannot use the d-test. Cannot use the d-test for constrained optimization. And I want you to remember that because the d-test is used to assess whether something is a relative min or max across the entire surface of that three-dimensional function. So no, this point is not in fact a maximum of that entire yellow paraboloid. The max we observed is somewhere up here, a little bit higher, but because we're constrained to only producing 20 units, this is the best point that we could possibly find, this 5, 15, 19,950. So we see that this is a two-dimensional, what we would call two-dimensional cross-section. And what it looks like is something like this. If we were to rotate that graph, we would see that this was our point 5, 15, 19,950. So the way we'll check if this is a maximum is we're going to pick test points. So let's look at a couple of points surrounding this point 5, 15, 19,950. Now this is just a two-dimensional representation of a three-dimensional function. But I'm going to pick a point that's slightly to the left and slightly to the right and just check to make sure that that yields a smaller profit subject to that constraint. So our constraint, recall, is this x plus y, the total number of units produced has to sum to equal 20. All right, that means if I pick something over here, let's say that this is going to correspond to an x value of 4, well, I can't just pick an arbitrary value of y. Now, 4 was kind of arbitrary. I could have picked 3 or I could have picked 4.5, anything that's slightly to the left of x equals 5. But 4, 27 is not going to be a point that is valid because 4 plus 17, 4 plus whatever I said, 23 is 27, and that exceeds our constraint. So if x is 4, if x equals 4, then that means that 4 plus y equals 20, and that means that the y value would be 16, because remember, they need to sum to 20. So 4 and 16 would be a valid point. And then what I would need to do is compute the corresponding profit of that point. So now that I have 416, I am going to compute the profit at the point 416, which will be a matter of plugging 4 and 16 back into our objective function. So negative 4 squared plus 20 times 4 minus 100 minus the square of the y value plus 40 times the y value minus 400 plus 20,000. And what I'm looking for here is for this to yield a value that is smaller than the profit of 19,950, which is what I'm claiming to be my max. Now, if plugging this all in, we get $19,948, which is clearly a profit that is smaller than 19,950. So that's a good thing because that seems to convince us more and more that 5, 15, 19,950 is in fact the maximum profit that we can yield. But just to be sure that this graph doesn't start to increase on the opposite side, because there are ways to have a zero slope, right? Like something like that, where there's still a zero slope here, and the profits could be less on this side, but they actually could be greater on the other side. So what I'm going to do as well is verify that this point right here, which is a point that's slightly to the right of x equals 5, so maybe x equals 6 would work, or 7, or 10, or anything beyond that, no more than 20, of course. If I had 6 units, if x is equal to 6, then in a similar fashion, I could say 6 plus y has to equal 20, which means that y would equal 14. Again, they have to sum to 20. 6 plus 14 is 20. And I'm going to compute the profit at this point. So in a similar fashion, I'll compute the profit of 6 comma 14. And that's going to give me $19,948. And this is happening because of the symmetry of the curve. It's a parabola is symmetric with respect to the where the vertex is located. And so this is again smaller than our max profit of 19,950. So my conclusion is that 5, 15, 19,950, $19,950 is the max profit for x equals 5 units and y equals 15 units. And that's really where our optimization problem stops. We're done now. We've achieved the end outcome. But this is an important phase in general in verifying that what the mathematics has found is in fact what you were hoping to find. Because imagine that you work for a company and you're trying to maximize profit and you go through all of this, but what you've actually located is a minimum. That's not going to be good. No employer would be happy about that. So that concludes this particular problem.